Morning, everyone. You got Joe Schoon over here from Fluid Numerics, and today we're going to be talking about building a continuous integration pipeline for containerized Fortran applications using Google's Cloud Build. Today we'll be going just a little bit over what continuous integration is, and I'll walk you through a really simple example from an actual Fortran application that we're currently working on. So let's just go ahead and get started. So first I want to talk about what continuous integration is very briefly, just to get everyone on the same page here. So essentially, continuous integration is a development practice where developers will integrate or push code into a shared repository very frequently, usually multiple times per day. And when they push to that centralized Git repository, the idea is we want to have some type of automated mechanism called a trigger to execute a consistent build pipeline that always makes sure the application can be compiled, that the compiled application can then run and of course get the correct answer. And then usually in the event that all those things happen, we want to publish some type of artifact, and this could be just the binary of your application or a set of shared object files that are just kind of tarred together for distribution. It could be a Docker container or a Singularity image or a virtual machine image. But essentially, this is what we want to have in place with an application that's underneath continuous integration, so that we always have a consistent way to make sure things are working, or we can just catch bugs early before they actually go out for deployment. So let's talk a little bit about what a build pipeline should do. Essentially, a build pipeline, again, should answer the questions: does my application build? Does my application run? And does my application get the correct answer? Now, with compiled applications, and specifically when you're writing scientific software in high-performance computing, in this day and age particularly, we want to make sure that all those questions answer positively on a range of hardware. You might have certain customers or use cases where serial CPU application builds need to run and get the correct answer. Of course, this is always a good thing to make sure your application does. And then you might have, in the case where you might have MPI or OpenMP, that parallel runs maybe on a single VM or a single node or multiple nodes also gets the correct answer, maybe also performs well. So it's not maybe just about getting the right answer, but it's maybe meeting some performance requirements. Now, outside of just the CPU side, of course, everyone's paying attention to GPUs these days for scientific applications. They're becoming more popular for some of those compute-intensive applications like computational fluid dynamics, molecular dynamics, and what have you. And so in that realm, you're starting to get into this area where we also have to start testing applications on single GPU platforms, where you're compiling your application to run on just one GPU, or multi-GPU, where you're doing a combination of MPI plus CUDA or MPI plus HIP or OpenMP or OpenACC. And of course, in the last couple of years, this has been getting even more complicated because now more vendors are coming to the stage with their own GPUs. So it's no longer just can we get these answers correct on just on NVIDIA platforms. AMD, of course, is coming into the center of the stage with the Exascale project coming out. And then, of course, Intel has their own line of GPUs. And with that, you have a range of possible ways to program them. And so doing this build pipeline is getting really complicated really fast. Although we want to answer these three basic questions, we have a lot of different hardware and incantations or flavors of these applications that we need to build and test for. And, of course, doing all that manually, it can be very time-consuming. And we don't necessarily want to have developers focused on, every time they're trying just to do something, to focus on running all those tests themselves. What we want the build pipeline there for is to be able to automate that process and report back to the developers what's working and what's not. Okay, so what does it take to build an application? So to answer this question, does it build? Let's talk about some of the ingredients for building an application. Specifically, we'll think about Fortran or C++, in general, just compiled applications. So something where you want to turn source code into an application binary, or even a set of libraries if your job is really developing some sort of middleware for end users. The first thing we want to start with is a consistent build environment, and what this means is you want to make sure that all the developers on your team are always starting from the same point, usually the same operating system, maybe the same set of system dependencies that are already in place. Now, if you have a shared cluster in your organization, this is usually accomplished that way. Usually through things like environment modules. You can agree in your team which environment modules to use, so that way you know you're always using the same compiler, same MPI flavor, and the same set of software dependencies that are pre-built and ready for you to use. Going forward, especially as you get towards cloud environments, and certainly you might think of customers who might not have that exact same environment, you want to be able to build in that environment that is going to be as close as possible matching where your application is going to run in production. So one solution for having a consistent build environment is to use containers. Underneath containers, there are a couple providers that I'll just call out here that are fairly popular: Docker and Singularity. And again, all these do is just make sure everyone is starting from the same operating system, the same set of dependencies before you actually build your application. So there's no longer this issue of, well, it works on my machine, but it doesn't work on someone else's. And of course, once you build your application inside of there, and if everything tests in that environment, you can certainly turn around and ship that Docker container image or that Singularity image to your end customers. The other option that we've seen coming up, especially in the cloud environments, are virtual machine images. These are just things that can be deployed to cloud environments, or if you have on-premise, if you're working with VMware or hypervisor or some other type of hypervisor and you want to create virtual machine images. Again, the whole principle is the same. You're starting from the same operating system, the same set of dependencies, and some of the tools there to help you with that, if your application is not container ready, are Vagrant and Hacker. Okay. So once you have this consistent build environment, most applications, and the Fortran applications certainly, have some type of make system. Again, this is just something that has a set of instructions that can be used to turn your source code into libraries or a binary or a set of binaries. The most common thing folks use is what's called a makefile. And then, of course, for portability, without thinking about containers or VM images, some folks look at other systems. I like to call them meta make systems, like CMake or AutoConf. Now, what these systems do is they will go through and detect what operating system and some of the other hardware features on your platform, maybe even look for some of the package dependencies and where they are, and they will make a makefile for you. And then you can execute that makefile to actually install your application. If you've worked with some legacy code out there, I'm sure you've seen it. If you're working in Fortran, you might have also seen a set of bespoke shell scripts that go through some build process. And usually these scripts appear for teams that are really trying to be portable, and so they're basically setting up a whole set of options to change out compiler tool chains, so that maybe in some they want to offer builds for GNU and Intel and LLVM compilers, and on different hardware. Maybe you want to have MPI only, MPI plus OpenMP. They try to put all those options into some set of scripts, but generally you'll see that's kind of the ecosystem we have for make systems out there. And then the last thing we need to really support that build pipeline are the build instructions. And what do I mean by that? Because most of those build instructions really are encapsulated inside of that make system, but really by build instructions what I mean are the set of commands you need to run to invoke that make system in that build environment. So for example, if I were to say, hey, my build environment is Docker, my make system is a make file, the build instruction that I need to run is Docker build. And that would go through the process of actually creating my application. Of course, if you have bespoke scripts, you're going to have your own set of custom commands to build your application. If you're CMake, that's going to be that you're going to run the CMake command, and then you're going to probably run a make install. If you're in AutoConf, that's going to be your configure, make install pipeline for your build instructions. So you kind of get the idea. Okay, so those are the three ingredients. We got a consistent build environment, make system, and the build instructions. Usually, in some way, all of these things are encapsulated in code that are stored in your repository. For Docker, you would have a Docker file. For Singularity, you'd have a Singularity image file. For Vagrant and Packer, usually it's a YAML or a JSON file that specifies some of the steps there to specify where you're starting from, what things to run to get your application to build. Okay? So the next question we need to answer, or let's talk a little bit more about what it takes to test your application. So when we want to answer the question of, does it run, does it get the right answer? And in this realm, I really just want to focus on really two different types of tests that are out there. We have what are called integration tests, and I call those out first because this is the most common thing I see in Fortran applications and in a lot of research groups. And then we have unit tests. So real quick, integration tests, you can, I guess the most common example of this is, that I'm aware of, is, in space weather and meteorology and oceanography and those types of realms, folks will put together, a set of code to solve some type of fluid dynamics problem, and they'll create a set of, test case examples that they go through and do scientific validation on. And they get the code to a point to where they know, hey, all this source code, all these subroutines pieced together in this way with this set of input creates a validated scientific output, and they establish what's called a gold standard. So when you go to use an integration test to test your application, what you're doing is you're invoking large sections of the code to run. Okay, so it usually invokes large sections of the code to run pre-configured, validated test cases. Okay, so you're not able to necessarily test, individual sections of your code, but you're kind of putting it all together to solve like a physical problem. Okay. Usually what this means is, when you do this, is it requires that you compare the output with a validated gold standard. All right, and some cases, I've seen folks, particularly when we get to the portability problem, not all compilers will give you the exact same answer, especially if you're using some aggressive optimization flags. And so when you're comparing with a gold standard, usually there's some allowance for tolerance that's there, and that has to be that decision of how much tolerance you allow for a solution to deviate as you change hardware, as you change compiler tool chains and such. That has to be done very carefully. And it has its own nuances on how you choose to do that. Now on the other side here are unit tests. Now unit tests specifically look at testing individual routines by varying the inputs over a range of valid possible values, or over the range at which you expect the end user to actually make use of that routine. So if you have 3 inputs, for example, into a subroutine, A, B, and C, you would call that subroutine varying A, B, and C over a whole range of values that make sense. And when you run that routine, you would expect to know what the behavior of that routine is supposed to be and what output it's supposed to produce. And by basically, toggling through all those possible options, you would determine yes or no, is this routine running properly? So it does. So a unit test, it tests individual routines over a range of known and varied input, and compare, and it just and then we check the behavior or the output with something that we know is the exact right answer. And this can be a little bit more challenging, and it does require that you know in detail some of the behaviors of the algorithm that you're implementing, and it certainly requires a little bit more work than just doing an integration test, but it can certainly pay off in identifying specific bugs. For example, if an integration test fails, it might be challenging to figure out where specifically in your code things are failing. In a unit test, you'll be able to know right away, because you'll be able to know which routines are causing a specific problem. Now, in general, in practice, it's a good idea to have a mix of both of these in place. One, because the integration test might highlight some things, that you would not catch in a unit test. You might think in the unit test design you didn't cover all possible bases, when when you're varying the range of all the input parameters. So in general, it is good to have a range of these two different types of tests. Let me finish this note here. So we got to validate against known, so we'll say well-known output and behavior. And of course today we'll talk a little bit about what that means for our example. So today's example, we're going to be looking at an application called the Spectra Element Libraries in Fortran. This is a mixed language. It's primarily Fortran for all the CPU code. If you want to find it, it's up at github.com/fluidnumerics/self. This is an application we're working on. Essentially what this code does is it gives you a way to numerically estimate derivatives, so divergence, gradient, and curl for scalars, vectors, and tensors in 1, 2, or 3 dimensions. So it's meant to be a library that's used for solving partial differential equations. And in our case, so again, the language is Fortran with a little bit of C, actually C++, and where that comes in actually is for the GPU acceleration. We're using AMD's HIP platform, and specifically the HIP-Fort wrapper to be able to expose HIP kernels into Fortran. And today we're just looking at, so the target platforms for today's example are just going to be serial CPU only, because we are just getting started with setting up our continuous integration platform. This is a good place to start because it reduces some of the complexity with setting up this pipeline. Next week we'll be adding on to this build pipeline to show you guys how to test out GPU accelerated apps on Google Cloud. Okay, so in addition to the platform here, what else do you need to know? The make system. Today we're using just a make file that comes with the code. So no CMake, no autoconf, none of that quite yet. And then on the, what else do we need here? For the build environment, we have Docker. Okay, and then of course for our build instructions, what we're going to be using to set up the steps it takes to run or to build and test our application, that is going to be Google's Cloud Build. All right, so if you're looking to do this for your application, the first thing you want to answer are these basic questions here. What platforms am I looking to target? What make system am I using? What build environment do I want to use? And what build instructions? I highly recommend going the containerization route, but of course there are other options. But once you get those answers, that's really going to set the stage for what you're going to do next to build your CI pipeline. And of course, if you're going with Google Cloud Build and Docker, a lot of what I'm doing today will translate well to your project. So let's just go ahead and get started with the example today. What we're going to do now is just review the Spectra Element and Libraries in Fortran repository, just to show you what we have set up there to make this build work. And then we'll go through the process of creating the build instructions with you, and then we'll test out that CI pipeline. So let's hop on over to the Google Cloud Console, and to get there you'll just go to console.cloud.google.com. Okay, and once you're there, what we're going to do is head on. Actually, what we need to do first is go ahead and activate that Cloud Shell. So the Cloud Shell is just a build environment that you can use. It's just a Linux terminal in your browser that will allow you to hang on a second here. I'm having a few technical difficulties on my side. Okay, that's better. All right, so we're going to go to our Cloud Shell. Again, this is just a Linux terminal environment. It has Git, Docker, and a lot of the tools we're going to need today, specifically the gcloud SDK. This is what's going to allow us to manually test out our build pipelines. Once you're in there, it should automatically set to the project that you're actively working on. If you need to change that, you can just use the gcloud config set project and then put the project inside of there. Now I've already cloned my self repository up to this shell. So this environment gives you about 25 gigabytes of home directory space, and of course, like I said, it connects you to all the Google Cloud's resources. Now let's take a look at what we have inside of here. So I have, of course, my Docker file, and I'll quickly review that with you guys. Let's take a look at that source directory. So again, that source directory's got a mix of F90 code, so Fortran, and C++ for our GPU kernels. And then we have in our home directory our make file. I've called it self.make. And then we have this ci.sh. So now I just want to review with you what each of these do and how they fit together into our build and test pipeline. Let's take a look at self.make. Again, if you've written a make file, you already know where this is going, but essentially what we do is we specify the compilers, the libraries, or the linker flags, and the includes flags all up in here, and then down below we have all the instructions to turn each one of our bits of source code in. What I'm doing here is creating object files and then linking those together to create just a shared object library. Okay. Now, the deal is all those paths that are referenced inside that makefile are going to be the paths that are used inside the Docker container. So if you haven't used a Docker container before, essentially what's going on there, you can think about it as you're getting a fresh operating system, and it's going to be a different set of directories from what you're working on here in the Cloud Shell or on your own terminal environment. Let's take a look at that Docker file. So what basically the sort of layout of a Docker file is you tell Docker what container image you want to start from. In this case, I have a custom Docker container image called self-dep or self-dependencies that provides for me. I believe I'm building on Debian. Actually, yeah. This is a Debian image that has Rockham installed, so AMD's Rockham, so that I get access to HIP-CC, and HIP-FC. And then I have the NVIDIA drivers also installed in there. So that Docker container will actually allow me to run on both AMD and NVIDIA GPUs. And then down below, we just have all the instructions for actually building our application. So what it's doing here is it's actually pulling in the current directory. So the directory for my whole source code recursively is copied into the directory TMP inside the container, so that I have all that source code available to actually do the build process. Down below, I'm actually building a few dependencies that self needs. So FEQ parse is an equation parser. We have JSON Fortran, so I can work with JSONs inside of Fortran, read and write. And then I have flap, which does a lot of argument parsing for us, which I'll show you why that's important in a minute here, because I actually use argument parsing with a binary to control our continuous integration. Now down below, and I'm actually basically I go into that temp directory and I run make install using that self.make file that I've copied in, and that's pretty much it. Okay, so remember, so now you got the idea here. So I've got my source code and what the build system is going to do. If I were to run Docker build, it's going to use that Docker file to pull in all that source code into the container. So I have my consistent build environment, and it's going to run through the make process to build my application. Now, once it's built, I have a binary called self, and I want to make sure that that thing runs. And it runs successfully. It gets the right answer, and this is where that ci.sh file comes into play. So as I mentioned before, this particular application does a lot of things. You can do, if you put in an input set, if you put in some nodal values of a function on a grid, you can interpolate that to another grid. You can calculate the divergence, gradient, and curl. Of course, depending whether you're a vector, scalar, or tensor, those operations mean different things. But essentially, you can do calculus operations. Now, of course, since it's all done numerically, those are all estimates of those operations. They're not exact. Now, what I've been able to do is use spectral element theory to put upper bounds on the errors for computing a divergence. So I guess I kind of need to give you a little bit more context. So when I put a set of nodal values for a function on a grid, the number of degrees of freedom, or the amount of actual data I put into this, determines what that error is actually going to be. The more data I put in, the lower the error, of course, until I get down to machine precision round-off errors. So what I want to be able to do in my test, and the way I've designed it, is I want to be able to call each one of these routines. So in this case, we're looking at the vector divergence. So if I put in a vector field on a grid, and I calculate its divergence, I should be able to put an upper bound on the error. And that's what I have here specified in the command line option for tolerance. In this case, I'm just doing the divergence of a constant vector, which we know should be 0. So anything else other than 0 is technically error. So what my test routines will do is they will set up that grid of vector functions, in this case a vector of 1s. It will use the self routine to calculate a vector divergence, and then it will calculate the error because I know what the exact value should be. And then, of course, if the error comes out to be larger than this tolerance, I would throw a non-zero exit code, and that test would fail, meaning that subroutine is not working properly. Now, I know this is not going to be specific to your application, but this kind of development is what a lot of developers actually need to do to really complete the other half of building that CI pipeline. It's not just about writing the routines that do the thing. You also have to write your tests and then find some way to include them in that build pipeline. So it can be a bit of work, but once you start getting moving in that direction, you'll find that your development process can speed up dramatically. So if you're paying attention to the number of lines I have down here, these are pretty. This is quite a bit of tests I have here. I think all told, right now I'm in at about 122 tests. And of course, right now I'm running everything with no GPU acceleration. So right now, that's all I have. Now, of course, once I go to GPU acceleration, that's going to double the number of tests I have to do. And as I increase the range of hardware that I want to test on, I just have to repeat all these tests over and over and over. And by the end of this, I think with the range of hardware we're trying to target, which is a fairly wide swath of NVIDIA GPUs and some of the more modern Radeon and the MI series GPUs from AMD, we're looking at close to 1,000 tests to run on every commit. And of course, having a developer do that it's a lot. It could be a lot of work if it's done manually. So once you get it scripted up and you get it into your CI pipeline, you should be good to go. So that should give you an idea of what we're doing for building and for testing. Let's talk about how to write that cloudbuild.yaml file to set our build instructions here. So if we're using Google Cloud Build, what we're going to want to do first is in that root directory of the repository, open up a file called cloudbuild.yaml. Okay, and let's go ahead and just pull this up to keep it from being so distracting. And there's two main sections we need to include here. So we have the steps. So this is going to be the section that specifies the actual instructions, what we need to do to build and test our application. And then down below we have images. And so particularly if you're creating Docker images, this is what you'll include down below, because then when you're done, all those images that you create during the process, the Docker images, can get posted to a container registry, which allows you an easy option to share that artifact, that image containing your application with your end customers or other collaborators. Okay, so let's talk about the steps here. Now, to specify a step, there are three basic fields you'll want to specify every single time. You'll have an ID, we'll have a name, and we'll have an argument. So the ID is just a human readable name for that particular build step. So here we're going to say build self. Okay. Now I want to give you a little bit more context now into what Cloud Build actually is. So Cloud Build is a serverless solution for doing continuous integration pipelines. How it works is each one of these steps that we put in there are actually going to run inside of a Docker container in that environment. And now for this first step, we actually need to run Docker. So what's really going on Cloud Build is Cloud Build is going to launch a Docker container that has Docker installed so that we can run Docker build. So what goes into this name field is actually the name of a Docker container, a public Docker container that you can reach to execute that particular build step. So here we have GCR. If you want to use the Google provided containers, and there's a handful of them available directly from Google, you'll use gcr.io, which stands for Google Container Registry, and then Cloud Builders is the public project that Google has available for you to use any of these publicly available builders. And then for us, we need to use Docker. Definitely take a look through the Google Cloud Build documentation. You'll find it very easily if you just look for Cloud Build in your favorite search engine. Perhaps it's Google. There's a few available there, and of course, if you can't find me in that list, there's a very nice repository of community contributed cloud builders, including things like Singularity, etc. Okay, so the name again specifies a container in which we want to run this build step in, and now we just need to give the arguments that we want to pass to that container. Now in the Docker build step, the entry point or the command that it assumes you want to start with is Docker. So all we need to do is pass in the arguments that we want to send to Docker. So you have build, since we want to run Docker build. And if you used Docker before, you know the next argument is a path that contains the Docker file and all the other files that are going to be used in that particular build. And then we want to tag an image, so we'll use the -t flag. And here I'm going to make an image. Now I want to post to my Google Container Registry in my GCP project, so I'm going to use gcr.io. But now I'm going to use project ID. The environment variable. So there's a handful of free environment variables you get for free when you're running Cloud Build. Project ID will fill in with your current GCP project ID. Of course, if you had a specific project you wanted to point to, you could just put what that project ID is there directly. It's really up to you. And so I'll say self, and then we'll do, for now, we'll fix the tag. Next week we'll get into more things like substitutions so that you can dynamically change maybe the Docker container tags or the VM image names and things like that. So that's really it. That's all we need to do the build. And then down here in images, what we're going to do is publish gcr.io self fluids self dev. And this just makes sure that the image, let me go ahead and unindent that, it should be all the way over. This will make sure that the image is available in our Google Container Registry when this build is done. So we have that publish step in our build pipeline done from there. Now if you have other artifacts like a Singularity container image, again, check out that Google Cloud Build documentation. You can use what's called the artifact registry. It operates very similarly to the container registry, but you can post more general objects, including things like Singularity images. Okay, so with that done, the next thing we need to do is specify the test step here. So again, we're going to do an ID, a name, and we'll do the arguments. So in this case, I've created a Docker image. Now I want to test self. In order to run this application, what I'm going to do is use gcr.io cloud builders /docker. Okay. And in this case, what I want to do instead of build is I want to run the application. So to do run, I'm going to do that, and I'm going to specify the name of the image that we want to use, or the container image that we want to use. So self dev, okay. And then the commands we want to run are bin/bash,
And then in my case, I want to run that ci.sh file. Now I've set up my build system to actually put that ci.sh file inside the container at the path apps self bin ci.sh. So that's about it at this point. I think we've got our 2 tests here. So a couple things to keep in mind when you're running on Google Cloud Build in that serverless environment. The default, you get access only to 8 virtual CPUs. This is 8 hyperthreads. You have 2 other options. I believe you can go as high as 64 virtual hyperthreads, so it's like a 32 core machine. But there's no GPUs available. So like I said, next week we'll have to touch on how to connect to Google Compute Engine so that you can do tests on GPUs, or maybe even you want to do higher core counts. You want to run an MPI test at scale to test your application. We'll talk about that next week. Just keep that in mind. The only other limitation to be aware of is the default timeout for this build. So these build steps will run by default for 10 minutes. If the build and the test takes longer than 10 minutes, this build will actually fail. So the way you work around that is you add the timeout specifier, and you'll specify the number of seconds that you might need. So in my case, the starting image that I use, it's pretty hefty. It's Debian. It's got Rockham. It's got the NVIDIA toolkit. And the CUDA drivers inside of there so that I can build for both AMD and NVIDIA platforms. It's also got other things like HDF5 and a few other tools. So it's fairly large, and it takes about 5 minutes to actually pull it down before I can even start building. This is pretty typical for HPC applications. They just tend to be fairly hefty containers. And then, of course, my tests, they do take a few minutes. I think all told, these builds in general range from 10.5 minutes up to 15 minutes. So I'm going to go ahead and just be safe and put this at a half an hour. So we'll say 1,800 seconds. So we should be good. With that cloudbuild.yaml now in my home directory, you can run gcloud build submit to manually test that. Give it the path where everything is that you want to bundle up. Essentially, what's going to happen here is whatever path you specify there, everything underneath is going to be recursively bundled together into a tar file, uploaded to the Google Cloud Build service, where everything will run. And then, of course, I like to use the async flag because this gives me back my terminal. Go ahead and authorize. Once this builds, I'll walk you through what you can see on the console, and then we'll go through actually setting up the triggers so that you can just push to a branch to trigger a build, and you don't have to use the gcloud build submit command. So if you go back into that console in the top left corner, click that products and services menu, and I pinned cloud build up here, but most of you will find it down underneath tools. So let's keep going. There's our cloud build. When you get there, you'll see the history if you have one. Otherwise, it'll default you to the dashboard. And now that we've started a build, so what you'll be able to see is every single build that's run in your project. You'll have that history here. Let's click through on this one since it's currently running to show you what you get inside of here. Of course, you have all the build logs, everything that's happening during that build process. Anything that goes to standard out gets written to screen here. And you have some more information on the execution details. Outside of what you can see on the panel, you can use the gcloud SDK to programmatically pull down logs and do other types of processing. But that's a topic for another day. That can become a very deep rabbit hole. So essentially what's going to happen here is this is going to run for, like I said, about 10.5 minutes. Right now you can see it's pulling down that Docker container that we need to start with, which is that self-fluids self-dep image, and it's going to build. So while that's going on, let's go ahead and set up some build triggers, and then I'll show you how that whole triggering system works. I'm going to show you today how to do the manual setup. Of course, in practice, what we actually like to do is use Terraform to set up infrastructure as code to programmatically set up those triggers. And that information is also stored in our repository. But again, that's a topic for another day, what we'll be covering this month. Okay, let's look at the triggers here. I've already got a couple in place. We're going to set up a new one. Okay, actually, I'm going to delete this one because this was from yesterday's tutorial, and I don't want it to interfere with what we got going on today. Let's go ahead and hit Create Trigger. Don't worry if you haven't connected a repository. You'll be able to actually do this if you're following along through this step here. So let's say what we want to do is a dev builds trigger. So, we like to follow a Git flow development strategy where we have a main branch and a develop branch. Here I'm going to set up a set of triggers to to operate on the develop branch here. So for the events, you have 3 types of events that can cause a build to happen. It's a push to a branch, push of a new tag, which is you can filter out which branches and which tags you want to build with this trigger by using regex statements, which we'll do below. And if you have a GitHub repository and you've connected your GitHub repository with the GitHub app through Cloud Build, you can also enable builds when pull requests occur. The nice thing about the GitHub app too is the information that comes from Cloud Build, the pass or the fail, will also post back to that GitHub, your GitHub's page, which is nice, so you can see the statuses of each commit on your GitHub site, which is pretty cool. Okay, so for the source, if you hit that drop-down menu, again, if you haven't connected any repository, go ahead and connect that repository now. I've already connected mine myself through the GitHub app. And then for the branch that I want to build develop. Again, this is a regex statement here that's going to filter only, that you want to set up to filter only branches of a certain type. Of course, if you have feature branches, you might do features star inside of here. And that way it would build all feature branches. It's really up to you and your team to decide when to build things for your project. Now, if you put that cloudbuild.yaml in your root directory and you've called it cloudbuild.yaml, you can just leave this at auto detected. If you put it elsewhere or called that YAML file something different, you'll want to click on that Cloud Build configuration and specify the path. I'm going to go ahead and leave it as auto detected. Okay. So we've got dev builds. Let's go ahead and down here in our repository, let's create a branch. Actually, I think I'm already on a develop branch. Cool. So at this point, let's add that cloudbuild.yaml. Let's commit, and let's say demo commit, since this is just for the demo. And we'll say push u, since this is a new branch on my repository, origin develop. It's a new branch on the remote. Okay, so now that I've pushed up there, let's go back to the history. And you'll see now we've got a new build that's getting provisioned, and it's using that dev build trigger. Okay, so that's really it that I wanted to walk you through. I mean, we covered a lot of ground in terms of just setting the stage for what continuous integration is, what you need for building. Remember, that's a consistent build environment. You need a make system, and then you need some way to encapsulate the instructions required to build your application. For testing, remember, there's a lot of heavy lifting that needs to be done on the developer side to develop what tests you're going to do, whether they're integration or unit tests, and then you need to have some type of scripting mechanism to actually run those tests and determine whether or not those tests are passing or failing. Once you have all of that, you can encapsulate all those steps into a cloudbuild.yaml to run through the build, run through the test, and publish that image if everything passes to your container registry. Next week, what we're going to be looking at is how to add tests for GPU accelerated apps, just single GPU accelerated apps, and we'll cover a bit more details on container registries and the interactions between Docker and Singularity using that container registry. So I hope you guys found this useful. Thanks again for tuning in, and we'll catch you next week.